Welcome to this particular module. In the last module what we have seen? We have seen what are the silicon wafers and what is a clean room and what is a gowning procedure for working in a clean room environment. In this module let us see the application of silicon dioxide in a integrated circuit industry, and then we will look at the op amps. Alright. So, if you see the slide, when you see application of silicon dioxide in IC industry, what you see that depending on the thickness of oxide, the application of oxide changes. If it is 1 micrometer, then we use this as a filled oxide. If it is 0.1 micrometer, it is a masking oxide. So, let me give an example of a masking oxide. Once we look at this. So, then you have from 10 nanometer onwards we have pad oxides, from 1 to 10 it is gate oxides, and then you have a chemical oxide from chemical native oxides. For the depositor oxides you have back end insulators between metal layers, and then you have a masking oxide. So, let me, like I said, give you an example of the masking oxide, right, and what I will do is I will open a PowerPoint, and what I will show you today is that how can we use silicon dioxide as a masking oxide. Silicon dioxide as masking oxide. All right. So, I have a silicon wafer, all right. What I want is a pit in a silicon dioxide. This is silicon wafer, silicon wafer. I want to etch silicon wafer. This is my final device, final device, all right. How can I fabricate this kind of device? For that I have to protect this layer and this layer, right, from etching. So, what I will do is I will grow a silicon dioxide, Now, depending on the type of growth, the silicon dioxide will either grow on both the sides or on single side. If I use thermal oxidation, I can grow silicon dioxide on both the sides of a silicon wafer. Now, I will protect silicon dioxide in this area and this area with the help of photolithography. All right. What will happen is that I have to use a photoresist, spin coat on the wafer, use the mask, expose with UV and protect the photoresist only in this region. What do I mean? Let me just quickly draw it for you, so you understand. If you see my earlier courses, you will understand how the photolithography works. Okay. This is silicon wafer, this is oxidized silicon wafer, this is oxidized silicon wafer with photoresist, all right. Then on this I have to do pre-baking called soft bake. After soft bake, I load the mask. Such that assume that there is a positive photoresist. Positive photoresist characteristics that the unexposed region will be stronger and the exposed region will be weaker. All right. This is my mask. Okay. This is positive photoresist. Now, I will expose this wafer with UV. When I expose the wafer with UV and I develop the wafer, when I develop the wafer. So, I expose the wafer with UV, unload the mask and develop the photoresist, that is called developing of wafer. Then what will I have? I will have photoresist only in this region. You got it. So, this is a process for, so my photoresist will be saved only in this region. Now, this is what is shown over here, right. After this I will dip this wafer, dip in SiO2 etchant, right. If I dip the wafer in SiO2 etchant, my SiO2 etchant is buffer hydrofluoric acid or hydrofluoric acid, generally buffer hydrofluoric acid is used. Then what will happen? The silicon dioxide will get etched in this region, will get etched in the region which is not protected by my photoresist, like this, okay. And then I can etch silicon wafer. So, after this I can remove my photoresist or strip off my photoresist by dipping the wafer in acetone. If I dip the wafer in acetone, then I will be able to remove the photoresist or strip of the photoresist from the top of the silicon dioxide, and then I will dip this wafer further into silicon etchant. Now, there is a dry etching, there is a wet etching. If I put in KOH or TMAH, right, it will start etching silicon and I will end up with this particular device, right. So, what will happen still that when I etch it, if I keep this wafer, in silicon etchant, what will happen? You know, this will happen, this will happen. But what I want just silicon, right. So, after this if I dip the wafer in BHF again, what will happen? Silicon dioxide will get etched and I will end up with this one. So, the point that we are making here is that silicon dioxide will act as a masking oxide when I want to etch silicon only in a particular area, which is right over here, right. The process is you take a silicon wafer, grow oxidized silicon wafer, right, or grow oxide, and then on that you spin coat photoresist, do a soft baking, load the mask, expose with UV, then unload the mask, develop the wafer, right. After developing the wafer you can do a hard bake. If I go as per the process, after hard bake I can remove my silicon dioxide with the help of SiO2. When I etch my silicon dioxide, if I want to etch my silicon dioxide, I can etch my silicon dioxide with the help of BHF, and then after etching my silicon dioxide I can strip a photoresist by dipping in acetone, right. Once I strip the photoresist, the wafer will look like this, which is right over here, and then after that I can etch my silicon with the help of silicon etchant. In this case, when I am etching my silicon, my SiO2 will protect the remaining silicon surface except where it is not there. So, this means that silicon dioxide is acting as a mask for etching when we are going to etch silicon, right. And once we are done, we can dip this wafer in a BHF to achieve what we want here, alright. Again, a detailed photolithography process is shown in my earlier courses. So, just if you want you can just go through that videos and you will know it. Now, what we are going to see further is, so what we are seeing here is the masking oxide, right. Same way we can use as a field oxide, we can use as a gate oxide where there is a thin layer of oxide in MOSFET, and then what we see here that very good etch and selectivity between silicon and silicon dioxide. If I use HF, I told you hydrofluoric acid or buffer hydrofluoric acid, if I dip this wafer in hydrofluoric acid I will etch my silicon dioxide and I will end up with my silicon, right. So, if I dip this wafer in HF, then I will have my silicon, okay, because HF will not etch silicon, it will only etch silicon dioxide, or you can say there is a good etching selectivity between Si and SiO2. All right. Now, further, if I want to also dope the wafer, then similar way if I want to etch the silicon wafer, instead of that if I want to dope the silicon wafer only in this region, only in this region, right. Then if I have using lithography, if I protect this area, this two area, and I dope it, then my dopant will only reach in this particular silicon wafer, right. So, this is just a silicon substrate, silicon dioxide is shown in pink color. If I dope it, it will dope in the substrate. Now, depending on the type of dopant, whether it is boron or phosphor, you have to select the thickness of the silicon dioxide. Silicon dioxide mass thickness depends on the type of the material that you are diffusing. When you want to diffuse for let us say 10 hours, right, and it is boron, then you have to use close to, and if I have the wafer at 1200 degree centigrade, I need a thickness of close to 0.2 microns, right. So, this is the graph, this is the plot showing you that what time, with respect to time and temperature, what should be the thickness of my mask, silicon dioxide mask. Okay. So, if I have a lower temperature, then my thickness should be less. If I raise my temperature 12 degree centigrade, I require a thickness close to 0.2, but if I go for phosphor, my thickness should be even higher. All right. So, this is how the silicon dioxide mask for boron and phosphor will work. The point that we are making here is that silicon dioxide can be used as a masking oxide. Okay. Now, we already have seen that. So, let us see quickly operational amplifiers, and this is just knowledge that the first operational amplifier, the first patent actually for vacuum tube op amp was in 1946, where the first commercial op amp available was in 1953, and then first discrete IC op amp in 1961, followed by first commercial successful monolithic op amps in 1965, and then from 1967 onwards leading to advent of modern IC, we use even today the 741 generalized op amp, right. It is from Fairchild. Depending on the manufacturer, the symbol would change, the terminology would change. However, we will see that at the part of this course somewhere that what exactly mu A stands for, and how can we understand from that whether it can be a military grade op amp or it is a commercial op amp. Okay. Now, the quick way of identifying is there is a notch on the left side, there is a pin number 1 and it goes to pin number 8 if it is a 741 generalized op amp. Okay. Now, so the op amp have at least 5 terminals. There is a positive supply VCC, negative supply minus VCC or minus VE, there is a output terminal number 6, there is a inverting input terminal number 2, non-inverting input terminal number 3, right. So, 1, 2, 3, 4 and 5, at least 5 terminals are used. There is another terminal between 1 and 5, and that is for offset. We will talk about that later, and then there is a 8 which is for not connection, right. So, between 1 and 5 there is offset null and 8 is not connected. Now, the input, if I apply input at the inverting terminal, my output would be 180 degree out of phase with respect to input. If I apply the input signal to non-inverting terminal, my output will be in phase with respect to input terminal. Okay. The op amp is fabricated on a tiny silicon chip and packaged in a suitable case. Fine gauges wires are used to connect the chip to the external leads. We already know this. Now, if I go further, op amp is a very high gain amplifier fabricated on integrated circuit, combination of many transistors, FET resistors in a pin head space. It finds application in audio amplifier, signal generators, signal filters, biomedical instrumentation and numerous other applications. Alright. The advantage of op amp over transistor amplifier, we have to understand, right, why we have to go for operational amplifier over transistor amplifier. So, operational amplifier has many advantages such as low power consumption, it costs us low, it is more compact, more reliable, higher gain, and it is easy to design. Okay. These are the advantages of operational amplifier over the transistor amplifier. Alright. So, let us understand till now for this module about the advantages of operational amplifier of transistors. In the next module we will see further on the op amp. Till then, you take care. I will see you in the next class. Bye.